Greetings AP Stats, Mr. Eicher here to look at 2010 AP exam question FRQ number 4. Automobile company wants to learn about customer satisfaction among owners of 5 specific car models, A, B, C, D, and E. Large sales volumes have been recorded for 3 models, and the other 2 models were recently introduced, so their sales volumes are smaller. The number of new cars sold in the last 6 months for each model is shown in the table below. The company can obtain a list of all individuals who purchased new cars in the last 6 months for each of the 5 models. The company wants to sample 2,000 of these owners. So part A, for simple random samples of 2,000 car owners, what is the expected number for model E and the standard deviation for model E? Excuse me. So when you see expected number, that's another word. Expected value is another word for the mean, and the standard deviation is obviously the standard deviation. This would be mu not x bar and sigma not s. This is the population parameter. This is the entire population. So in several random samples, many random samples of 2,000, on average, how many would you expect to be model E? Well, first let's find what percentage was model E. So if we took 23 of that model and divide by 297,354 total, we get 0.00781. So as a percentage, that would be 0.78%, so less than 1%. If we have samples of 2,000, then our mean would be n, 2,000, times the proportion that we're expecting. So this is basically a binomial distribution. It's binomial because it's either E or not E, E or not, so B for binary. We can assume independence because of the 10% condition. 2,000 is less than 10% of the entire population. We have a fixed number of trials. Fixed number of trials is 2,000. And we have our probability of success. We have our probability of success, which was 0.00781. So this is a binomial scenario. Oops. So our mean would be if there are 2,000 cars and in the population there is 0.00781, we would expect then not very many, only 15.6, and it's okay to leave the decimal there. You probably should leave the decimal there. So we're expecting 15.6 Model E cars. And the standard deviation on the formula sheet, the standard deviation is provided. So let me show you that. On the first page of the formula sheet, in this table right here, we have the second cell says binomial. And then that second row has mu x equals np, and then sigma x equals square root of np times 1 minus p. So those are the two formulas for the mean and the standard deviation. So let's go back here. So we have our standard deviation is the square root of np 1 minus p. So that would be the square root. Maybe I'll call that standard deviation of model E. Do this as the mean of model E. There we go. So we have 2,000 cars. We have the probability of 0.00781. And then 1 minus 0.00781. and that would be our standard deviation for the number of Model E cars that we're expecting. So calculating that, I get a standard deviation of 3.94 Model E car. So on average, the number of Model E cars typically varies from the mean of 15.6 by 3.94 cars. So that was question A and B. Let's look at part C. Oh, sorry, that was question A. Let's look at part B. So I'd like to do part B in two ways. The first way is, since we just mentioned that this is binomial, let's see if we can answer this question as a binomial probability. We're asked what's the probability in a sample of 2,000, same as part A. How likely is it that we get fewer than 12? So we want what's the probability that we get fewer than 12 out of the 2,000 that are sampled. So fewer than 12, that's basically asking us what's the probability we get 0 Model E, or 1, or 2, or 3, or 4, all the way up to 10, 11, 12 Model E out of 2,000. So, fewer than 12. I guess I should be careful about that. Fewer than 12 wouldn't actually include 12. Fewer than 12 would be 11 and down. So to calculate this, we would calculate, you have 2,000, choosing 0. The probability of Model E that we had earlier was this probability, raised to the 0. 1 minus that. To the 2,000. Plus, so that's the 0 case. We have to do this 11 more times. That would be a lot to do. So maybe I'll just do plus dot dot dot. The last one you'd have to do is 2,000 choose 11 with 0.00781 to the 11. 1 minus 0.00781 to the 1989 equals, and then that would be our answer. Now there's a calculator shortcut that would make this much, much easier. The calculator shortcut, we would write binomCDF, since we have a range of options, not just 0, but 0 up to 11. That's a continuous range of integers that we want to calculate. So our n would be 2,000. Our probability of success of getting a Model E car is 0.0781. And x is, how many successes do we want? Now again, binomCDF goes from 0 up to the number you tell it, x. So we want to go from 0 all the way to 11. So let's see what that looks like when we go and calculate that. So we have second vars, binomCDF. Our sample size is 2,000 cars randomly selected. Probability of Model E is 0.0781. And the x value is fewer than 12 would be 11 and down, so 0 to 11 is what this is going to calculate. And our answer is 0.146. 0.146. 0.146. So that's the probability that we get at least well, probability we get from 0 to 11 owners of Model E car in the sample. That's one approach. I actually want to show you an extension to this approach. So if we go back to our calculator screen, if you'd like to see all those particular probabilities, probability of 0, and then 1, and then 2, if we go to second, not second, if we go to y equals, and if we type second vars, and do binomCDF, because we want to see the particular ones, our sample size is 2,000. Our probability of success is 0.00781. And our x value will leave just as x. And again, we're using this x up top by alpha. And hit enter. And that'll type it all in there. And now if we just look at our table, so if we go to second window, which is the table setting, it says TBL set above, set your table. And we'll start it at 0, and we're counting by ones. And the independent and dependent variables automatically are calculated for us. So then to look at the table, instead of hitting graph, you'll hit second graph, which says table above it. And here are the probabilities. So what's the probability of getting 0 Model E? It's that. Probability of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if we were to add up all of those, we would get that 14% number. So that's about 6. It's about 4, so it's 10, that's 12, 13, 14-ish, so about 14%. So that's a handy trick that you could use to calculate binomial probabilities by typing binomCDF into your y equals menu. You just have to be familiar with looking at the table and how to set the table before looking at the table. Okay, so that's the binomial probability approach. That answer that we got, that 14.6%, 0.146, that's the exact answer. Now, in question A, we had just calculated the mean and the standard deviation. So if we can justify that we could use a normal curve, then we can use a normal curve to approximate this answer. So let's look at another approach on how to answer this one. So let's clear this. And now let's try using a normal approximation. To a binomial distribution. To justify using a normal curve, we have a condition, n times p has to be greater than or equal to 10, and n1 minus p has to be greater than or equal to 10. This is the exact condition that you saw many, many times doing confidence intervals for a proportion, doing significance test for a proportion or difference in proportions. So in part A, we had calculated this n times p to be 2,000 times 0.00781. If I remember, that was 15.6. That's greater than or equal to 10. And then 2,000 minus that would be the number of failures. That equals, mental math, 844, I think. That's also greater than or equal to 10. So since both are large enough, both successes and failures are large enough, we can use a normal curve, a normal approximation. Let me give you another visual of this, why that n times p greater than or equal to 10, what that looks like as a histogram. So this is on Statlet, binomial distribution applet. I typed in 2,000 for n and 0.00781, and I plotted the distribution. Now, since we have so many possible number of successes, and our probability was so low, it kind of shifts it down here. But I'd like to notice, hopefully we can notice If we zoom in some, it's really skinny, but this is a normal distribution. So I can click on this Show Normal, and it doesn't do very much, but if we continue to zoom in, can't zoom in anymore, that is actually a roughly normal distribution. Now let's say we didn't have a large enough sample size. Let's say our sample size was 10, and plot that distribution. That is definitely not a normal distribution. But as we increase the sample size, that's about a half of a normal distribution, maybe. Try 500. Yeah, so since our probability of success is so small, let me just change that. There you go. So with a small sample size, we get a not normal, that's a left skewed distribution. But as you increase the sample size, it becomes gradually and gradually and gradually more roughly normal. But that's all based on the interplay between n and the probability n times p. So n times p there would be greater than 10, and n times 1 minus p would probably also be greater than or equal to 10. So that's just a visual for this problem that we're working on right there. So if we are going to use a normal approximation, we've just justified right here that we can use a normal approximation. So we'd have a normal curve from part A, and from right here we have the mean is 15.6. From part A we had calculated the standard deviation to be 3.94. And we want the probability of 12. 12 is about 1 standard deviation away. 12 or fewer. And that would be finding the probability. The z-score is less than 12 minus 15.6 divided by 3.94. On the calculator, that would be doing normal CDF. The lower bound is, I guess, technically 0, but since it's a model, we'll just put negative infinity. The upper bound is 12. The mean is 15.6, and the standard deviation is 3.94. So using the calculator, we can calculate this probability to be second vars, normal CDF, lower bound, the upper bound is 12, the mean is 15.6, and the standard deviation was 3.94. So our probability is about 18. That seems pretty different from what we had earlier. I think earlier we had from the binomial probability, we had, what, about 14 or 15? 14.6%. That's different because this is an approximation. Something that we could do to try to fix this approximation is if we want less than 12, technically I guess we should have 11 here. And that gets us a little bit closer. It's a little underneath what it should be. But maybe we could make this a 0 since we had, context that we really want 0 to 11. See if we get a little bit. Okay, that didn't do very much, did it? And then there's something else called continuity correction factor that isn't part of our curriculum that would make this closer to that 14.6. So I think the answer that we had, the exact answer was this. But the answer that we got from that binomial, or the normal approximation was that. So it's about 3% off. But again, mainly that's due to trying to take a discrete distribution where you have 0, 1, 2, 3, 4, and putting a continuous distribution and finding all the area between those particular discrete values. But either way would be accepted on the AP exam as long as you justify that you can use a normal distribution like we did right here. So that's another approach for Part B that I wanted to share with you. And then lastly, let's look at Part C. Part C says the company is concerned that a simple random sample would include fewer than 12 owners of model D or fewer than 12 owners of model E. Briefly describe a sampling method for randomly selecting 2,000 owners that will ensure at least 12 owners from each of the 5 car models. So I've included here all the car models so we can check those out. So their concern is pretty justified. We're just using finding probabilities, and there's what, a 14.6% chance that we'd get fewer than 12 of model E, and maybe the company doesn't like those chances, so they want to make sure they get at least 12. So one approach that you could do, maybe I should say the main approach, to make sure that you get to ensure at least 12 from each type. They're doing a sample of 2,000 and they have 5 types. So if they took 400, a random sample of 400 car owners of each of these types, that would ensure that you get at least 12. This would be called a stratified random sample. Stratified random sample is that you divide them into similar homogeneous groupings, which they already are based on car model, and then you take a simple random sample within each group, within each stratum, so 400 from each. So this would guarantee that you're still doing a random process, that you're getting at least 12 in each. Now maybe a stronger response, a better response, not that it's more correct, but maybe a better idea, rather than taking the same amount from each one, maybe we could take a proportional amount from each one. So if we calculate the proportion, I remember that E was 0.00781. But if we find a proportion of each amount, so A is 112,338 divided by 297,354, 30, so this one is 378. So that's the proportion of model A in the population. And then the other ones would be these. And those all should add up to roughly 1, maybe not exactly 1 due to rounding. But then what we could do is do, for model A, we need 2,000 cars times 0.378, and that would equal 0.378. That would equal, we need to sample 756. So in our random sample, we would take all these Model A car people, and we need a sample size of 756 of that particular model. And then we can continue with each of the models. Model B, 2,000 times 0.323. So we need 646 Model B. And then repeat for the other car models. For other models. So the key here, a couple keys, you want to make sure that you mention this is a stratified random sample. You want to describe it well enough so we can tell that you're still taking random samples but from within each car model. And then lastly, for full credit, whatever sample sizes of each model that you have to make sure that they're all at least 12. So whether you do this proportional way or whether you just say, hey, let's just take 400 from each model, 400 of A's, 400 of B's, etc., as long as you ensure that you're getting 12 from each model, that would be essentially correct. Thank you for watching this video.